In the last module, we had started our discussion on logic synthesis. In this module, we'll continue the discussion further. We said that the basic steps in logic synthesis are state reduction, state encoding, state assignment, choose resource types in terms of flip-flops and gates, and then derive flip-flop input equations, output equations, and then minimize the logic expressions that are obtained, and after that obtain the final gate level circuit. This basic design procedure is essentially the same as any digital sequential circuit design procedure that is taught in basic digital electronics courses. And in fact, the example that I took in the last module were from Maurice Mano's famous book, Digital Design. So, although the essential design principles remain the same due to the sheer size of VLSI circuits, here there are many different types of algorithms applied. For example, one of the places where various kinds of heuristic algorithms are applied is in logic minimization. So, when the number of input variables, when the Boolean expressions become huge, the Carnot map based logic simplification does not suffice anymore, and specialized computer aided design tools are required to conduct these simplification procedures. Today we will discuss two-level logic minimization. So, we understand that any Boolean expression can be represented by a two-level logic expression. Here we have two levels. The first level is an AND plane, the second level is an OR plane. So, there will be numerous product terms, and there will be an OR gate which will sum up all the product terms together to realize the final function. However, we often do not use two-level logic expressions because many a times these are practically unrealizable. There could be an arbitrary number of literals in the fan-in of an AND gate, and we may not practically have an AND gate with that many input available. And therefore, we need to use multi-level logic expressions. Moreover, although the delay, which is primarily represented by the number of levels, is lowest in two-level logic expressions, the area consumed is many a times very huge, where the area of the corresponding structural representation here is denoted by the number of literals in the Boolean logic expression. So, many a times multi-level logic expressions are used in place of two-level logic expressions. However, two-level logic expressions are still important because within these multi-level logic expressions, two-level logic expressions are required. Hence, we will study here the simplification procedures for two-level logic expressions. Now, what are the objectives of two-level logic simplification? The objective of two-level logic simplification is to minimize the number of AND terms. So, we want to minimize the number of AND gates, and also to minimize the number of literals, as we said, that is the number of inputs to the gates. There are different methodologies applied for two-level logic minimization. The first, which we all know and we have studied, is the Carnot map method. Many of us have also studied the Queen-McCluskey method, and what we will study today is almost a standard tool which is used in VLSI design in logic synthesis. This is called the espresso algorithm. It's a heuristic algorithm for two-level logic minimization. A brief review of the Carnot map method is as follows. We choose a one which is not already covered. Then we find maximal groupings of ones and don't cares adjacent to that element. We repeat steps 1 and 2 to find all possible maximal coverings. From these all possible maximal coverings, we choose the minimum set that covers all the ones. This is the way Carnot map works. What is the problem? What is the basic problem of the Carnot map method? The number of cells in the K-map grows exponentially with respect to the number of input variables. For n inputs, we require 2 to the power n cells. Moreover, it is difficult to visually represent a function which consists of more than, say, 4 variables, because the number of cells becomes very huge, and therefore simplification using this method is difficult for a large number of variables. This minimization procedure is used usually when the number of variables is small. Before proceeding further, we will understand a few basic definitions. First, the definition of a minterm. What is a minterm? A minterm is a product term in the sum of products expression, with all n variables present either in true or complement form. So a minterm is a product term where we have all the variables of the function present either in its true form or in its complement form. What is an implicant? Two or more product terms, which could be minterms as well, may be combined to get a product term of reduced size that covers both the product terms that were originally there. So two or more product terms may be combined, right, to produce a product term of reduced size, such that this new product term covers both the original product terms, right? So this is called an implicant. If the term is of size n, it covers one square in the Carnot map, right? If it is a minterm, it will cover only one term in the Carnot map. If it contains n minus 1, if the term is of size n minus 1, it will cover 2 squares in the Carnot map. If it has n minus 2, right, if the term is of size n minus 2, it will cover 4 covers in the Carnot map, and so on. Now we come to the definition of a prime implicant. If a term cannot be reduced further, then it is the implicant with minimum size. Why can't it be reduced further? Because if you try to reduce it further, it will cover, whenever we reduce a product term, it covers a few more cells in the Carnot map. And let us say, for this case, if we try to reduce this product term, it will cover a few cells not containing ones or don't cares. So it will contain a cover with some zeros in it, right? Which is not what is desirable. Which is not what is desirable. That is error. So if a term cannot be reduced further, because it will then cover some of the zeros in the Carnot map, then it is the implicant with the minimum size that is possible, right? And is called a prime implicant. So deletion of any literal from the prime implicant results in a term not covered by the same function. So if we try to reduce a prime implicant, what will happen is that the function will produce a 1 in some cases where it should not, right? So this is what is told when we say prime implicant, this deletion of any literal from the prime implicant results in a term not covered by the same function. Now we come to the definition of an essential prime implicant. A prime implicant is said to be essential if it covers minterms which are not covered by others. Let us consider the Carnot map, where what do we want to do? We want to cover the set of ones by a set of prime implicants, and we want to have the minimum number of prime implicants. When can we minimize the number of prime implicants? When we have a cover of essential prime implicants only, right? A prime implicant is said to be essential if it covers minterms which are not covered by others. this prime implicant possibly contains a set of ones which is covered by other prime implicants. But this prime implicant becomes an essential prime implicant when it covers at least one 1 in the Carnot map that is not covered by any other prime implicant. Then this becomes an essential prime implicant. Okay. Now we define what is an onset. Minterms which are 1 when the expression is 1. So onset represents the set of minterms which are 1 when the function itself is 1. Okay. Offset, minterms which are 0 when the expression or the Boolean function is 1. DC set, minterms representing don't care terms. So their values don't affect the output of the function, meaning that we don't observe the output of the function with respect to these minterms, right? Therefore they are don't cares. So then what is the basic idea of two-level logic minimization? The generic idea of two-level logic minimization is to find prime implicants and try to cover them using a minimal number of covers. This is what we said just now. The generic idea is to find prime implicants and try to cover them using a minimal number of covers. That is why we want to find out essential prime implicants, because it contains at least one that is not covered by any other prime implicant, right? Obviously a minimum cover will be a cover over essential prime implicants. So if now we take an example, a small example using the Carnot map method. So what do we do? Let us say we have a function which has these set of ones, zeros and don't cares which we represent here. Now firstly what we do, we try to find the cover over primes. So here is one prime implicant which cannot be extended further. Here is another prime implicant which cannot be extended further. Here is another prime implicant, right? Again, there are other prime implicants, for example here. So all the set of minterms which cannot be expanded further, right, by using only the ones and the don't cares form the prime implicants. Now we have other prime implicants as well. For example, this one is a prime implicant. This one is another prime implicant, right? Likewise, we find out all the prime implicants, and then from this set of prime implicants which we have been able to find out, we try to find out the essential prime implicants. For example, here these three prime implicants here, here, this one and this one. These three prime implicants are sufficient to cover all the ones in the function, and therefore it is a cover over essential prime implicants, and we do it through Carnot map in this way. However, as we told before, Carnot map is inefficient because when the number of variables becomes large, representing it visually through a map is very difficult. When we have n variables, we need 2 to the power n cells, right? So more than 5 variables, it is very difficult. For 6 variables, we need 2 to the power 6 equals to 64 cells. For 7 variables, we will require 128 cells, and so on. In the Quine-McCluskey method, we don't represent it visually in the form of a map. It's a tabular method. So what do we do here? Basically, I am not going to discuss the entire method here. I'll just explain what are the basics, fundamentals to this method. We determine all prime implicants like in Carnot map, but in a tabular form, and we consider all the ones and don't cares while determining the prime implicants similarly. And then we try to find a minimum cover, but using a tabular method. We have similar problems as we have in Carnot map method. because in most VLSI circuits that we have, in many cases, we have at least 20 or more variables in the Boolean expression. In the Boolean function, the number of input variables is 20 or more. In this case, we have to check 2 to the power 20 minterms, because Quine-McCluskey method is based on checking minterms. We have to find minterms and then cover minterm to form prime implicants, and therefore we have to check at least 2 to the power 20 minterms, which is huge. So therefore, we use better heuristic CAD algorithms. One of the standard tools that we use today is the espresso algorithm. We come to the end of this module with this discussion.